Oh, sorry I'm late. I was getting stuff ready to print off here for today. So, and I haven't printed it yet. That's the next thing coming. Well, I thought I clicked print. Okay, it's coming out of the printer. Today, we're going to be continuing along with stuff traveling in circles, but we're going to start considering a couple of types of acceleration that things traveling in circles will experience. And so one of the types is called centripetal acceleration. You may have heard of centrifugal force before, maybe. Turns out it's a fictitious force, but we'll take off from there today. Coast. So let's see, I need to bring that thing back up here. There I am. I'm forgetting where I am on these things. Okay, this one may, actually this we could do from what we were doing yesterday. A truck with 0.420 meter radius tires travels at 32.0 meters per second. What is the angular velocity of the rotating tires in radians per second? Well, yesterday when we developed some of those equations, we found out that when something is, I'll draw a circle first and then the other thing later. Whoops, I keep forgetting on this thing. Hold down this. I don't know why my pen is not working very well. Close enough. Okay, anyway, we'll just imagine that this thing has a radius r and it's rolling and turning in this direction with an angular velocity of omega. And this would be for something that's rolling, not skidding. But we found out that the velocity of this thing in this direction ends up equaling omega times r. Now, in this case, we happen to know the radius. We know that it's traveling at 32.0 meters per second, and that's close to 70 miles an hour, actually. So what's the angular velocity of tires in radians per second and revolutions per minute? Well, we just have to solve this expression for omega there. And remember, this is a Greek letter omega. And it will equal, let's see here, 32.0 meters per second divided by 0.420 meters. And unit-wise, we're going to end up with the meters dividing out, and we'll have just per seconds, but we put the radian in there. It's a placeholder word for that. So whatever 32 divided by 0.420 happens to be, we get about 70, we have 3 sig figs here, so 76.2 radians per second is what it would be. And then we're asked to cut that to revolutions per minute. So going from radians per second to revolutions per minute and vice versa should be something that you want to get comfortable with. So 76.2 radians per second first I'll do the revolutions. Well, 1 revolution means 1 complete turn of the wheel. That's 360 degrees, but it's also 2 pi radians. Remember that 360 degrees equals 2 pi radians, which means 180 degrees is equal to pi radians. Although in this case, we're going to do the other thing, but this is equal to 1 revolution. So that's what we want to use here. Now, the radians are up on top. I want to get rid of them, so I'll put the 2 pi radians on the bottom and 1 revolution on top. And that gets me part way there. The rest of the way for my version of unit conversion is to get rid of the seconds. And I know that 60 seconds equals a minute. So, and I want a minute on the bottom so that I'll have revolutions per minute. That's 60 seconds. So that'll take me to the other direction of the conversion. I think we went from RPM, revolutions per minute, yesterday, to radians per second. Now we're going the opposite direction. So times 60 divided by 2 pi. And I get about 728 revolutions per minute, which you can also call RPM. So that was not too bad, fairly straightforward problem. Now here's kind of an off-the-wall problem, but that's okay. Take the age of the Earth to be about 4.5 times 10 to the 9th years, and assuming its orbital radius has not changed and is circular, which is approximately correct for the Earth, calculate the approximate total distance the Earth has traveled since its formation. And this would be in a frame of reference with respect to the sun. So, goofy kind of problem, but I don't know. You can kind of imagine here that we've got Earth traveling in a circle around the sun, which is going to be right here. So that's the sun. In the classroom out at school, I have a scale model, sort of scale model of the Earth-Sun system, Earth-Moon-Sun system. And what I have is in the back of the room, I've got a yellow styrofoam ball hanging from the ceiling. And it's about, roughly the size of a tennis ball or a baseball. Excuse me, woke up early this morning. But anyway, it's tennis ball represents the sun, and up near the front of the room on a piece of paper, I have the Earth-Moon system. And on that piece of paper, the Earth is just a little dot about the size of the one that I stuck there, maybe a little bit bigger than that, probably closer to maybe that period that's right there. I'm not sure. But it's a dot, and the moon's orbit is a circle that's roughly that size as well. I think it's, or the moon's orbit, I mean. I think it's a little smaller than the size of the sun. But anyway, it's up at the front of the classroom, and for a Earth that's the size of a dot and a sun that's the size of that tennis ball in the back of the room, the correct spacing between the two is about right from the back of the room to the front of the room. And somewhere in the room, I've got a chart for that scale and asking the question, on this scale, where is the next nearest star? And this would be a star besides the sun, something that would be in the night sky. And people will guess when they see that. And almost never have people guess a large enough distance. Somebody will say, where the dormitories are, or something like that. And they're not very far from the thing. And then they'll get braver. Down at the little grocery store on Patton Boulevard, or somebody will guess maybe downtown Moses Lake, or downtown Ephrata, or the Tri-Cities. And that's about as big a guess as I've ever had anybody make, was the Tri-Cities. And on that scale, with a tennis ball sized sun, and something about this size representing the Earth in the center as a dot and the moon's orbit, and then let's see, this thing would be roughly, well, between 20 and 30 feet from the tennis ball sized sun. The next star would be about as far away as El Paso, Texas, and it would be another tennis ball sized object. And that's just kind of mind boggling to realize that. So something kind of neat. All right, but in this case, Earth is 4.5 times 10 to the 9th years old, and that means this is how many orbits it's made of the sun. And so that would be the number of orbits. Okay, now on each orbit, Earth will travel 2 pi r. That'll be the distance traveled, and that would be 2 times pi times the radius of the Earth's orbit, which you may have heard that it's 93 million miles, happens to be 150 million kilometers. Kilometers are kind of, well, they're a little bit smaller than a mile, about 6/10 of a mile, but that's okay. But it's also 1.5 times 10 to the 11th meters. Okay, that's how far it is traveled in each orbit. And so 2 times 1.5 is 3. So I could write for each orbit, I could call it 3 pi times 10 to the 11th meters. Okay, now that's not quite correct scientific notation to mix a pi into that, but that's how far we travel on every orbit. And then there's 4.5 times 10 to the 9th orbits that have been completed. And so the total distance in this case is going to be, let's see, 4.5 times 10 to the 9th orbits times 3 pi times 10 to the 11th meters per orbit. And you can see the orbits will divide out, and I'll end up with a number that's equal to some number of meters, and find out how far that happens to be. I'm going to multiply by pi and then by 3 times 10 to the 11th. And I get quite a ways. Okay, about 4.2 times 10 to the 21st meters. So quite a ways, actually. I have not much of a feel for how far that happens to be, although, let's see. I can kind of put it in astronomical terms, I guess. Let's see, times 600 times. Okay, so if I turns out that's actually about 45,000 light years. Okay, so if we'd been traveling in a straight line for all that time, we would have traveled, if we'd been headed toward the center of the Milky Way galaxy and didn't get absorbed by the black hole at the center of it, we would travel past the center of the Milky Way galaxy and be about 15,000 light years on the other side of it. So now it turns out that in addition to traveling around the sun, the solar system is actually orbiting the center of the Milky Way galaxy. So there are motions on motions on motions, but let's not worry about that one too much. Okay, this one is going to introduce the idea of something called centripetal acceleration, which I want to develop that idea first. And in the engineering physics class, when we study those students at the same time that they're taking physics, most of them are co-enrolled in calculus. And I know a couple of you have actually had calculus, but not all of you. So I'm not going to assume that knowledge, but we're able to develop this expression for a kind of acceleration that something undergoes when it's traveling in a circle. Now, one kind of acceleration that something can undergo when it's traveling in a circle is if you imagine something that's out on the rim of a circle, and if that object that's turning has angular acceleration, then the speed at which this thing is traveling along here, remember the speed is equal to r omega, but omega, if it's speeding up, this is one of those links between linear and circular motion, or yesterday I showed you this equation that if something has angular acceleration, which we denote with the Greek letter alpha, then its value of omega is equal to omega naught, what it is at the start of some time interval, or at time 0, plus alpha t. Well, I can take this and plug it into there, and the distance that something travels is then going to be r times omega naught plus alpha t, and it's going to be speeding up as it goes along. In its travel along the circular arc, it'll be speeding up. And we call that kind of acceleration that it's experiencing, in that case, tangential acceleration, because it actually has a direction. Its acceleration in that case is in that direction. And we call that A tangential. Okay, A sub tan. So there's that going on because it's on an object that's speeding up as it's turning. But there's another kind of acceleration going on because its velocity is changing. And if I draw the instantaneous velocity of the object, and by the way, I'm assuming that this thing is turning in this direction, in a counterclockwise direction, even if the circle or the thing that's on is not speeding up, it will still experience acceleration. This could be its initial velocity, and after some time interval, this might be, or as it's turned through some part of the circle, this will be its final velocity. And I could draw those two things right next to each other. And this will be the angle theta between where it started off at and where it ends up at. And it turns out that if I take those two velocities and put them right next to each other, and I'm going to make those velocity arrows the same length because I want to look at the particular situation where something is traveling with constant velocity. So here's V initial. Here is V final. And the change in velocity would be something that connects these two. This would be delta V. Now, something I can write here is that V final is going to equal V initial plus delta V. The final will equal the initial plus change, or V final minus V initial is equal to the change. But the change in velocity points in this direction. Now, if we consider shorter and shorter time intervals so that this angle shrinks down, this angle will shrink down. Turns out this is also equal to the angle theta because the instantaneous velocity is always perpendicular to a radius vector from the center out to here. It's a tangential, it's tangent to the path that it's traveling, what it is. Anyway, but as that shrinks down, we find out that this delta V ends up being perpendicular to the instantaneous velocity, and it points into the center of the circle. So when something is traveling in a circle with constant velocity, its total acceleration is in toward the center of the circle, and it's constantly changing direction, except that it always points to the center of the circle. Now, this is constant velocity. It could also have a tangential acceleration at the same time. But we're staying simple here and just imagine that it's moving with constant angular velocity here. All right, if we go a little bit farther with that, we'll find out, and we're not going to because it involves a bunch of algebra, but it turns out that that acceleration is equal to V squared divided by the radius of the circle. And we call this centripetal acceleration. And it is there anytime an object is traveling along a curved path, as long as it's not at rest. If it's at rest, it doesn't have this kind of acceleration, but it'll always be there. Centripetal is also sometimes replaced with the word radial, R-A-D-I-A-L, because it's along a radius of the circle, is what it happens to be. What else can this be called? Oh, the word centripetal means center seeking. And so, yeah, it points toward the center. It's kind of center seeking. It's an acceleration in that direction, but it's due solely to the fact that the object its velocity is constantly changing direction. Tangential all the time, but that change is always toward the center of the circle. If it wasn't experiencing that acceleration, it would travel in a straight line tangent to the circle and leave and not come back. And so this centripetal acceleration is due to the fact that it's traveling in that circle. Now, we can write this centripetal acceleration in another way if we use something that we saw yesterday, that V is equal to R omega. That would make V squared equal to R squared omega squared. And so this centripetal acceleration can also be written as R squared omega squared over R, because R squared omega squared is V squared, but R squared over R is just R. So we could write it as R omega squared as well. So that's a worthwhile formula to remember that it exists. You may not remember it itself, but if you print off your formula sheet, both of these should be on there for centripetal acceleration. So let's look at an example having to do with that. Olympic ice skaters are able to spin at about 5 revolutions per second. I don't know if you've ever watched the skaters in the Olympics, which are they simultaneously having the summer and winter Olympics? No, I think it's just the Summer Olympics in Tokyo this summer, maybe. There's still a danger of cancellation because of COVID. Japan hasn't dealt with it very well yet. Anyway, what's their angular velocity in radians per second? Well, 5 revolutions per second. You should be able to rattle this off pretty well now. I want to get rid of the revolutions, and so I'll put something on the bottom that'll take me from revolutions to radians, and 2 pi radians. And then, oh, that's all I have to do, because these are revolutions per second. I don't even want to think about spinning that fast. I do not deal well with being spun horizontally. Never have, actually. I can remember even in junior high school, I almost got sick. Well, I did get sick, but I didn't throw up being on a ride at the fair. And my body just doesn't like that stuff. Let's see, mode. I don't know why. Oh, I guess that's just something it did. Anyway, 5 times 2 pi, well, that would be 10 pi radians per second, but pi is 3.14. So if I just multiply 5 times 2 times pi, whoops, somehow I ended up with 52 times pi. That wasn't the intent. Okay, and that ends up being about 31 radians per second. So what is the centripetal acceleration of the skater's nose if it is 0.120 meters from the axis of rotation? Well, centripetal acceleration can be v squared over r, but we can also write it as r omega squared. And so in this case, 0.120 meters times that omega, 31 radians per second. And we'll see how the units turn out here. That omega has to be squared. Let's see, 0.120 times 31 squared. I'm just going to use the number that I have in my calculator for that. It's a little more than 31, but that's okay. And I get about 120. Okay, now unit-wise, I would have, let's see, meter radians squared per second squared when I square those units. But again, radian is just a placeholder word, and so I'll cross it out here, and the acceleration will be in meters per second squared. Remember, a radian, that angle in radians is an arc length divided by a radius, and this has units of meters, that has units of meters, and we call this ratio radians when we use it in this context, but there aren't any physical dimensions to it. So 120 meters per second squared, that's about 12 Gs, which is a lot, but it's only the tip of your nose that's experiencing that acceleration. The smaller r is, like going toward the center of your brain, the smaller the acceleration becomes. Okay, an exceptional skater named Dick Button was able to spin much faster in the 1950s than anyone since, at about 9 revolutions per second. I don't know anything about Dick Button other than this problem, and he always used to be one of the announcers on TV when they were doing the figure skating competition in the Olympics. So that's about all. He was able to spin at 9 revolutions per second. Well, his omega is going to be 9 revolutions per second times 2 pi radians per revolution. So he will have a greater angular velocity. Which ends up being about 57 radians per second. So the acceleration for Dick Button's nose, same 0.120 thing here, the centripetal acceleration, r omega squared and again, we'll end up with meters per second squared. And actually, I rounded a number up to get that 57, so it may not be quite as big as you would have thought otherwise. But now, this is a whole lot more than that happens to be. This isn't quite twice as fast, but it gets squared. And so this ends up being more than 3 times as much as that. And so that's pretty significant. But because it goes with the square of the angular velocity, a speed or an angular velocity that isn't, you know, this is only, well, it's less than twice as much as that. But when you square it, you get something that's more than 3 times as much as that. So that's the reason that that happens to be the case there. So pretty neat. Stuff like that. Okay, this is one of those rides that my body does not like. And a fairground ride spins its occupants inside a flying saucer-shaped container. If the horizontal circular path the riders follow has an 8-meter radius, okay, how many revolutions per minute will the riders be, at how many revolutions per minute will the riders be subjected to a centripetal acceleration whose magnitude is 1.50 times that due to gravity? Okay, well, we know what the acceleration is in this case. It's equal to 1.50 g, and I'm just going to use 9.81 for g. And I get 14.7 meters per second squared. So that's the acceleration they're experiencing. Now, I know what the radius of their path happens to be. So this acceleration will be produced by r omega squared. So far, I haven't even used a v squared over r, really that version of the equation yet, but this is equivalent to it. So that's why I can do that. The radius, I need to find omega first. And so omega squared will equal 14.7 meters per second squared divided by r, the 8.00 meters. And now I get a number here that's about 1.8. It just looks like per second squared, because if I imagine this thing on the bottom as a meter over 1, meters over second squared divided by meters over 1, bring that up and multiply by its reciprocal. And it looks like I just have 1 over second squared, but this is where I just take that placeholder word and stick it in there. This is omega squared, which is usually radians per, omega is usually radians per second, but if you square it, you'll have radians squared per second squared. And that radian is just a placeholder word, so it doesn't make any change in the value to introduce it or its square or anything else. But if I just take the square root of that, I will get some number. Let's see, raise that to the 0.5 power. And I get about 1.4 radians per second. And then this is wondering how many revolutions per minute will they experience. Well, I convert that into revolutions per minute. So I've got 1 revolution over 2 pi radians, and then times 60 seconds over 1 minute. Kind of repetitious with that thing. So the radians go away, the seconds go away, and I'll have revolutions per minute here. So times 60 divided by 2 pi. And I get about 13 revolutions per minute, which is going to be a little less than 5 seconds per revolution. Yeah, I know my body would not like that ride. Any questions on that one? A lot of unit conversion on this thing. Let's see, this has a bunch of unit conversion on it too. And actually, it doesn't actually have us do anything with the centripetal acceleration, although we could figure that out. So, yes, let's do that. This says, verify that the linear speed of an ultracentrifuge is about 0.50 kilometers per second, and Earth in its orbit about 30 kilometers per second by calculating A, the linear speed of a point on an ultracentrifuge, 0.100 meters from its center, rotating at 50,000 revolutions per minute. They must go that fast. Ultracentrifuges were in the news a few years ago because they're used for processing uranium to extract the, well, basically it was to get rid of the more massive uranium-238 and leave behind the uranium-235. That's a process called uranium enrichment. And uranium enrichment is necessary if you want to use the uranium either for fuel in a nuclear power plant, or you have to enrich it much farther. But if you want to use the uranium in an atomic bomb, you have to purify it or enrich it even more. So you have to get rid of more and more of the uranium-238. This may be completely Greek to you, but if you had a high school chemistry course, you might have learned a little bit about isotopes of different elements. And on Earth, uranium occurs in 2 isotopes. The most common isotope, which accounts for 99 point, I don't remember what all % of uranium, is uranium-238. And it has 92 protons and I don't know how many neutrons. I don't feel like doing it in my head today. Actually, it should be 146, but maybe I could do it in my head. Yeah, it is. It has 92 protons. In nuclear physics hieroglyphics, this is the way that we write things. Often we just put the U-238 and ignore this other stuff. But 238 is the combined total of protons and neutrons. And then uranium has 92 protons. If it didn't, it wouldn't be uranium. It would be something else. And since it has 238 combined protons and neutrons, it has 238 minus 92, or 146 neutrons. But there's another isotope of uranium that occurs, and on Earth, it's nearly all of the remaining atoms in a sample of uranium, and it's uranium-235, which still has 92 protons, but it only has 143 neutrons. And so that's proton number, that's neutrons, and this number up here goes by various names. It's sometimes called the mass number, because this is protons and neutrons are pretty much what contributes to the mass. Electrons, each one is about 1,750th the mass of either a proton or a neutron, so they don't account for much. Sometimes it's called the mass number. Sometimes it's called the isotope number. Sometimes, actually, in nuclear physics, we called it the nucleon number. A nucleon is a generic term for either a proton or a neutron. It's like calling it being a person. You're not specifying whether they're male or female, and that's what nucleon does. It just calls protons or neutrons nucleons. And so the nucleon number is the sum of those two. All right, but in this, in these ultracentrifuges, they spin them very fast, and the more massive particles tend to get pushed to the outside of this centrifuge. A centrifuge is something that spins things really fast. And the more massive ones tend to get pushed to the outside, and so you get rid of those more massive ones, and that leaves your sample enriched in the less massive one. And so ordinarily, this thing accounts for a lot less than 1% of the uranium in a sample. But when you get rid of a bunch of the uranium-238, then the proportion of this stuff rises. And you have to get it up to, I want to think on the order of 5% of this stuff in order to use the uranium fuel in a nuclear power plant. But you need to have it up some number of tens of percents in order to use it in an atomic bomb. And I don't remember the exact proportion for that. So that's what this problem's talking about. Well, not really, but it is talking about an ultracentrifuge. Okay, this would be omega at 50,000 revolutions per minute. And we can, some of the numbers have 2 sig figs. A couple of them have just 1 that we know of. We'll just round this to 1 sig fig when we're done. Omega is 50,000 revolutions a minute there. And, let's see. Whoops, I want to convert that to radians per second to be able to figure this thing out. 2 pi radians over 1 revolution, that'll get rid of those, times 1 minute over 60 seconds. And that'll be some number of radians per second. Okay, and I get something like, to 1 significant figure, it'd be about 5,000 radians per second. And so that's what omega happens to be. And the reason I wanted that is because I'm supposed to figure out the linear speed of a point on the rim of this thing. So V is just going to be omega times R. So it'll be that 5,000 radians per second times this distance. Now this is 3 significant figures, so they've got all kinds of mixture going on here, but we can't add significant figures. So we'll just have to take our 5,000 radians per second and multiply it by 0.100 meters. And I'll figure out the linear speed in this ultracentrifuge, which ends up being 500 meters per second. And because this has only one significant figure, doesn't matter that this has 3. When I multiply them together, I'm going to be down to 1. So 500 meters per second. That's the speed in of a point out there on the ultracentrifuge. Oh, and it says about 0.50 kilometers per second. Well, yeah, if I multiply this by 1 kilometer divided by 1,000 meters, 500 over 1,000 is 0.5. So yeah, I would get 0.5 kilometers per second. So I just verified that part. Earth in its orbit, about 30 kilometers per second. Well, I'm supposed to figure out linear speed for that thing. Here's the deal. For Earth, the distance traveled, the circumference of its orbit is 2 pi r. We already did this once, I think. Seems familiar. The r in this case is 1.5 times 10 to the 11th meters. I just happen to remember that. 93 million miles. You could look it up in the back of the book if you wanted, but so 2 pi times 1.5 EE11 is about 9 times 10 to the 11th meters, sort of close. The linear speed of the Earth in its orbit is going to be this circumference, the 2 pi r, divided by how long it takes the Earth to complete its orbit. Well, it happens to take 1 year, so we travel 9 times 10 to the 11th meters per year, which is a speed, but it's not the one we're after. We want to get this into kilometers per second. So I'll have to convert years, and I'll put 1 year up here and stick 365 days down here, and then multiply it by 1 day over 24 hours, and then multiply that by 1 hour over 3,600 seconds. Fortunately, I remember how many seconds there are in an hour, so I don't have to do that. So anyway, the speed ends up being all that junk multiplied together. Basically, you're dividing by this. Oh, and then I should multiply that by 1 kilometer over 1,000 meters, and then it'll give me 2 kilometers per second. So here's what we have. I'm going to divide by, all those things are in the bottom. I'm just going to wrap them in parentheses. Whoops, forgot the divided by symbol. Okay, answer divided by 365 times 24 times 3,600 times 1,000. And I get 30 kilometers per second. So I just verified what they were talking about. Now, this problem doesn't do it. We're about out of time, but let's calculate the centripetal acceleration of each of these things. So for the ultracentrifuge, A, centripetal acceleration, V squared over R, and I'm actually going to use the V this time. So, and I will use the meters per second, not kilometers per second. So 500 meters per second, and I square that, and I'll divide by the radius of that ultracentrifuge, which was 0.10 meters, or 0.1 meters, and I'm going to get a humongous number. So yeah, I'm going to keep it at 2 sig figs because it's halfway between a couple of things. I get 2.5 times 10 to the 6th meters per second squared. 2.5 million meters per second squared. And well, if you divide that by 10, you'd get about 250,000 Gs. It's what it is, which is a lot for an acceleration. And that means 250 times the acceleration due to 250,000 times the acceleration due to gravity. Oh man, that would turn anybody into a puddle, literally a human being into a puddle if you had an acceleration that great. No wonder it separates isotopes. All right, for the Earth though, the centripetal acceleration is going to be RV, which is actually a kilometer is 1,000 meters. So it's actually 30,000 meters per second squared up here, divided by the radius of our orbit is a big number, 1.5 times 10 to the 11th meters. And you should convince yourself that the units will end up being meters per second squared. So if I just take that 30,000, got enough zeros on there, square it, and divide it by, oops, missed the point, 1.5 times 10 to the 11th. I get an acceleration of 6 times 10 to the minus 3rd meters per second squared. Okay, that's only 6 millimeters per second squared is the acceleration. So this is quite a small acceleration of the Earth traveling in its circular orbit around the sun. So a couple of centripetal acceleration examples, and I should have written this A equals V squared over R equals that thing, because that's what it is. Okay, your introduction to centripetal acceleration. And you experience centripetal acceleration every time you're in a car and you round a turn. You're experiencing centripetal acceleration continually while you're doing that. And so there's something that shows up. Hey, does anyone have any questions? Oh, I posted a new assignment on Sapling yesterday. And this will be the last assignment before our test. I also posted a test review assignment on Sapling, and after I did it, I realized that there are actually some common questions to the two. At least one, there may be more than one, but the test review questions are extra credit. The regular Sapling homework is not extra credit. You have to do that. So check that stuff out. And tomorrow we'll go on and talk about centripetal force, which is the force that is necessary to produce a centripetal acceleration. And so we'll carry on with more of this kind of motion.
Is the test on Monday? Oh, Mr. Ham, you're muted. I still can't hear you.
Oh, can you hear me now?
Yeah.
Okay, I don't know why it muted itself for a while and then unmuted itself, so whatever. But I don't, anyway, I'm planning on having the test on Tuesday right now. So I'm pretty sure I made that homework due Monday, although I'm not positive about that. But something like that. Anyway, go ahead and check out that homework. And we'll probably have a test review on Monday then. So over this Newton's Law material. Okay. All righty. And see you tomorrow.